In this video, we're going to do example 2.1.2. And here we're told the line L, xyz, is minus 3, 6, 1 plus t times minus 1, 0, 2 if t and r is given. We're asked in part A to write L in parametric equation form and in symmetric equations form. And so we have to remember from the previous video how to do this. Parametric equation form we read by components. So x is minus 3 minus 1 times t, and y is 6 plus 0t, and z is 1 plus 2t with t and r. And that's all there is to it for writing in parametric equation form. Symmetric equations form, we solve all of the variables for t and we set them equal. So all of the equations for t and we set them equal. So x plus 3 divided by minus 1 would be equal to t. Y has no t, so we'll hang on for that for just a second. And z is z minus 1 divided by 2, that's equal to t, so those are equal to each other. Since y has no t, we just write it as an afterthought. So those are the symmetric equations for the line L. Now part B asks us to identify a point on L and a vector parallel to L. So we have to remember again what we saw in the last video, which is what we can see in the line equation. This here, this was the position vector of a given point P, that was OP. And this was what we called the direction vector, which is a vector parallel. So in fact, part B is really just a matter about reading the equation as it's given. So if we draw ourselves a little diagram of L here, we can see point P and we can see vector OP. So this is joining to the origin. This is our point P and a direction vector D here. And so our point P is given by its position vector as minus 3, 6, 1. And we can see a vector parallel. We can see the direction vector as D as minus 1, 0, 2. Now the next part, C here, asks us to give 2 more points on L. So let's just remind ourselves of what L, the equation of L, was. And to give 2 more points on L, well, we have to remember that this here was the position vector of any other point, right? And this is the position vector of any point on L. And so what we have to do is just choose values for this parameter t to find some more points. So let's let t be equal to 1. And if we do, then we're going to get the position vector xyz is minus 3, 6, 1, plus 1 times minus 1, 0, 2. That's going to give me the position vector minus 4, 6, 3, which means that the point minus 4, 6, 3 is on L. And that is true for whatever value I choose. If I choose t equals 0, I'm going to get the point that I can already see. So let's choose t equals minus 1. Any choice of t will give you a point on L. So if I put in minus 1 here, I'm going to get minus 1, 0, 2. So now I'm subtracting, so I'm going to get minus 2, 6, and minus 1 as the position vector. So minus 2, 6, minus 1 as a point is on L. Now, so that was C, and then D, give 2 more different vector equations. Well, this, remember, this is the position vector of any known point. This is any vector parallel. And so I just take any point that I've got. Well, I just happen to have 2 lovely new ones right here. And any vector parallel is going to be any multiple of the direction vector that I can see. So I can do that really easily. Right, this is to make you notice that vector equations are not unique. They're not unique. They can look actually quite different. So let's use the negative here. So 0, minus 2 for t and r. That's a valid equation for L as well. And here, so is this. If I use the other point that we just found, its position vector, minus 2, 6, minus 1 plus t2. I could use d, I could use any multiple of d. So let's do 2 times d this time. Minus 2, 0, 4 for t. And these are both valid equations for L. Okay, let's go on to the next. So now we are given 2 more points. We're given points A and B, and we're asked to determine if they are on L. Well, the A and the B, right, these are the X, Y, and Z. So we're going to be checking whether they fit here in this equation. So it's easiest if we go and rewrite our equation for L in parametric form. So X is minus 3 minus t, Y is 6, and Z is 1 plus 2t. And then we plug in the X, Y, and Z for A and B. So let's start with A first of all. So we are going to check whether minus 2 is minus 3 minus t, y6 is 6, well that one works, and z, what do we have here, minus 1 is 1 plus 2t. So what I'm going to do is solve for t in each case and make sure I get the same value of t. So if I solve for t here, I'm going to get t is minus 1. And if I solve for t here, I'm also going to get t is minus 1. So these are the same value of t. There's a single value which makes this equation work, this system of equations work, which means that the system is consistent. Right? The single value of t works for everything, and if the system is consistent, that means our point A is on L. So let's double check with our point B here and see what happens. So our point B, if I plug in the x, y, z, I'm going to have minus 7 is minus 3 minus t. Y6 is 6, well that still works. And Z8 is equal to 1 plus 2t. Let's solve for t in each of these cases. So what am I going to get here? If I add 3, I'm going to have t is 4 from the first equation. And the second equation is going to give me t is 7 over 2. Well, those are two different values for t, and that cannot happen at the same time, which means that our system is what's called inconsistent. And you'll see those words more in your chapter on linear systems that's upcoming. So if the system is inconsistent, that means the point, our point B, is not on L. F, find all of the intercepts of L. So intercepts, this is something that you may not have dealt with in 3 dimensions. The x-intercept is when y and z are 0, so x, 0, 0. Similarly, the y-intercept is going to look like 0, y, 0, and a z-intercept will look like 0, 0, z. So what we have to do to find this for each of these intercepts is to plug in NC to see if we can solve just like we did in part E for each of these. So we are going to, for the x-intercept, we are going to let y and z be 0. So if we plug those into the parametric equation form again above, we get 0 is equal to minus 3 minus t. 0 is equal to 6. Well, that doesn't work. I don't even have to do anything more. This is inconsistent. 0 certainly is not equal to 6, which means that there is no x-intercept. Let's do the same thing for the y-intercept, which means that we are going to let x and z be 0. Again, we'll plug those into the parametric equation form. So 0 for x is minus 3 minus t, y is 6, and 0 is equal to 1 plus 2t, so this has a possibility here. Let's just see what happens. Here we will get t is equal to 3. Here we will get t is equal to minus 1/2. That is not possible. Again, inconsistent. And that tells us that we have no y-intercept. So let's check finally our z and see what happens. So for the z-intercept, we have to let x and y be 0. Again, back into the parametric equation form. 0 is minus 3 minus t. 0 is equal to 6 for y. Again, right off the bat, inconsistent. I don't even have to check the last equation. This will never work. And so that tells me that there is no z-intercept. And that is something that might be a little surprising to you. In calculus and in high school, it was very unusual for a line not to have an intercept. In fact, a line in R2 must hit at least one of the axes. It must. But in R3, a line might not hit any of the axes at all. So that's a little bit of a foreshadowing of what's coming next, that there are things that behave maybe a little bit differently than you have seen before, because R3 is much bigger. There's more space around for the objects to live in. Now, we have one last part to our example here. This is G. We're asked to give a vector equation for a line L2 that is parallel to L and passes through the point C. So let's do a little diagram here. We know our L. Here, let's have our equation of L brought back to us. We know our equation. This had OP here, so our point P. This is our direction vector D. This is our equation of L. We want another line L2. We want it to be parallel to L, but we want it to pass through the point C instead. So to create the equation, vector equation of a line, we need any point on the line. Well, we've got one, right? But we also need a vector parallel. We need any point on the line, and we need any vector parallel. So obviously the point on the line has been given to us. The vector parallel we have to find. Well, it's kind of staring us in the face, isn't it? If D is parallel to our first line L and L2 is parallel to L, then we can use our direction vector. Oh, that was hard to say. We can use D as the direction vector for our second line as well. So this is going to be minus 1, 0, 2, and that means the vector equation for L2 can be given as x, y, z is equal to pi e minus 1, the position vector of point C, plus t times minus 1, 0, 2 for some t and r. Now that's only one out of infinitely many possible ways of describing that line, but that is absolutely a valid equation for line 2.